We should just catch it.
Throw it right now. We want to sell. How do you make the design completely yourself? Like you came up with this
battle axe, dude.
What if I think it was like a battle thing?
What is that? A boomerang?
No, Brady, it wouldn't hit him. It would just come right back to you.
You know one of those throwing hatches? No, it's like
Throw it out.
well, it's a technically fake AirPods.
Right, like your shotgun.
I didn't get it. I already canceled it.
I got it.
Yeah, they picked up his AirPods.
Saturday.
I got it.
But it hurts after.
Wait, you got your?
I got the first two.
Yeah.
The first shot.
I didn't
I think I'm sister. Isn't it like 16 and older now?
Mm-hmm. So I was able to get it. You don't feel it. It's like, it's. I think it makes your arm big.
Yeah.
It's worse than the flu shot on the sore. It's kind of weird. Yeah, no.
What the hell's this?
I was gonna fail it anyway. Yes.
What did you get, Riley? Maybe you literally got like fifth highest score. You did? No, I got like I got second. But what did you get? 90. You said you failed it. I guarantee you. I didn't do those. I
That's basically my entire.
I left half. I didn't know any of the vocab.
You know what I do? I read it and then I'm like, oh.
You know, I was talking to him. He was making fun of me for getting the 95 saying I was You said for 2 hours. 2 hours.
I might. I don't know.
Yeah, but I didn't study the predator and imperfect. I was like, what the heck were you studying for 2 hours? This is literally a predator and imperfect cat. I was studying for vocab. There's 5 vocab. There's 5.
So I'm not ready.
You studied it for 2
Hey, you
hours.
Jolly Rancher.
Same, I was scared at. Yeah, yeah.
Got him. Beat him up. Beat him up. Just throw it. Stop that.
I just gonna rest the shot.
Yeah,
I
put your
got
mask on.
this thing in the stack of passes at the start of the third quarter, and they're all gone.
Does the end break something? You break every one, don't you? Break his today.
I remember one day he went through 4 masks.
Yeah, no, because you broke one.
Oh, what a glorious, beautiful, wonderful day this is going to be. I just keep telling myself that. Exactly. That's what you got to do sometimes. Just keep swimming. No matter what. Just keep swimming. Okay, get that, delete those, don't care. Doesn't concern me. Attendance, boodly-doo. Start here in a second. Let's see. Sam, when can you take this quiz? You were here. Were you here Friday? You were? She marked you absent. Why in the world would she have marked you absent? I bet she meant to because Ryan Geiger was not here. He wasn't. And I bet she just marked the wrong person absent. So, yeah, that doesn't surprise me. I was like, when I saw it, I went, well, that's weird. Yeah, she's got you marked absent, but Ryan's here. So since that's wrong, I'll just go ahead. Was anybody else absent in here? Is anybody that's here today not here on Friday? Okay. So then, yeah, that was a mistake. All righty. Great. Thank you. Let me do this. Shop, dop, dop, do, 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 do. No, I don't want that. Start thinking about this beautiful weekend, something fun you did. You're going to share that. Okay, row number 1's here. Row number 2, we're missing Wetzel. Row number 3, we're missing Geiger. And row number 4, we're missing True. Missing True. That's so true. Okay. True. Boop. And true. Boop. 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 All right. Weekend. Something fun you did over the weekend. We're going to start here with Miss Stacy.
I went to my Aunt Lisa's birthday in Colorado.
Did you have an Easter egg hunt when you were there?
Yeah, every year she always meets everybody's age, and they have your name on it, and you're not allowed to leave until you find it.
And how many would that be? How many did you have to find with your name on it?
Just one.
Oh!
Your name, but like there's other ages, but everybody has their own age with their name on it.
If you find yours first, do you get a prize? No?
It's mainly little kids, but I found all the eggs with money in it, and I just hit them harder.
And then you went back and got them later. I know your style.
I didn't get them. I had to go back to my mom's, but I just hid them so the little kids can everything.
Gotcha. Caitlin. Family dinner? Very nice. Riley. Cool. Samo.
We had family over for Easter.
Family over. Ty.
Just stayed home.
Stayed at home?
Yep.
You have an Easter egg hunt? No. I was telling you, you can like this. You have dogs, I know.
Yeah.
I was telling my kids the other day when we first moved up here, my 2 oldest kids were like 4 and 2, I think. And we had a yellow lab, and we hid eggs outside. And we had a bunch of ground cover. There was an egg in the ground cover the kids never found. Didn't realize it. And like 2 months later, the dog ate it.
Oh.
Dog found it and ate it. And it was like, oh, that's not good.
If it's on the ground, they'll pick it up.
Yes, it was over with, man. That day was about a half hour. It was not good. So, all righty. Noah.
I just went to my grandma's house on Sunday.
Very good. Owen.
Saturday we did Easter at my house and had Easter hunt.
Had a hunt?
Yeah.
Very nice. Very nice. Mr. Wright.
So yesterday was her birthday.
What? How old? 16. Are you going to get your license soon or not?
I still haven't got my guns.
So I guess no, you're not. Okay, we can answer that.
Like I want to, but whenever like I intend to, I never do. So
Okay.
Also made a boomerang for a prototype boomerang.
A prototype boomerang?
Yes.
3 arms or just a regular, like a traditional style? Well, you got it right there.
Well, I only have to put the class.
Is this for physics class?
Revised negotiations.
Okay, cool. That's it right there.
Sort of. It broke.
It broke. Oh
I
no!
mean, it's okay because it's a prototype.
Right.
But like,
So that was it right there.
yeah,
So it's the part that you're holding, what you hold when you throw it,
yeah.
and it just snapped when you were trying to throw it.
Well, no, I threw it like a few times, and then when it hit the ground, it snapped.
Then it snapped off. Okay. Very cool. Very cool. How did it work?
I
Did it come back to you?
mean, yeah.
Great. That's
I
cool.
mean, it flew weird just because it's weird. But
That's okay. That's okay. No problem with that. Mr. Turner, you were late the other day. I'm just kidding. I don't care.
I went to my grandma's house.
Very nice. Krista,
I worked all Easter.
you worked? Oh man. Were you sharing a lot of smiles with people? Good for you.
There
Good.
wasn't a lot of them were out. There wasn't a lot of people there. We just had like a big buffet for
Okay, that's cool. McPherson.
I just stayed at home.
All right. Mercury, Ford, Lincoln.
I just spent time with my Easter.
And Dominianianos.
Absolutely nothing.
Nothing?
Yeah, nothing.
Did you enjoy doing nothing?
Yeah. Okay.
All right, that's cool. Nothing wrong with that. All right, so I have not, I mean, I just looked at these when I first got in here today, and I really haven't paid much attention to them. How, in general, it looks like everybody just kind of flipped it and finished it. Did you guys have plenty of time to finish this?
Yeah.
Yes? Nobody had like a bunch of blank spots when they were done at the end of class? All right. So we're going to be, so here, let me just give you kind of like the next two goals that we have, objectives. The next thing we're talking about here is graphs, okay? So graphs of sine and cosine in particular. We'll talk about tangent later, but right now we're going to be focusing on graphs of the sine function and the cosine function. Then we're going to move to solving trigonometric equations, okay? That will be the next step after that. All right, so that's where we're at right now is with these two things. So we're going to be graphing trig functions, sine, cosine. We'll talk about tangent as well a little bit. Those are the primary ones. We will only look at secant, cosecant, and cotangent and explain what's happening and why it's happening. You will not be required really to work with those so much. You'll be focused mostly on sine and cosine and a little bit of tangent, just recognizing a tangent function and giving some information about it. Then after that, again, we'll solve equations in here. We will go from easy equations to harder equations, okay? That's kind of the goal. I would like to have the graphing aspect done this week. 4 days, I think we can have graphing and understanding sine and cosine done this week. All right, and we'll talk about tangent as well. And then next week, hopefully we can start doing some solving equations. One of the things I'm going to ask you guys to do is I want you to start studying, and we'll talk about this when we're graphing today. I want you to start really knowing the sine values, the cosine values, and the tangent values of the familiar angles. And when I'm talking about the familiar angles, I'm talking about the angles off of the unit circle, okay? So you have the pi over 6 families, you have the pi over 3 families, you have the pi over 4 families, okay? So I want you guys to make sure you're starting to know those, kind of like you learned multiplication facts. I want you to know, like if I just say to you, what's the sine of 2 pi over 3? I want you to be able to just say to me, radical 3 over 2, boom, boom, slam, I'm done. That's the goal, is that you can just give it back to me when I ask you for a familiar angle, sine or cosine value especially. We're actually going to take timed quizzes on that as well. We'll do our first one tomorrow. It's kind of like just a trial. It won't be for a grade, but so you can see what I'm expecting out of you. And then we'll start doing them some for grades as well. Okay? So, having said that, anything you guys want to ask before we kind of move on here? Start. Yeah, I'm sorry, Stacey. That's right. Planning to put it on quarter 3. Okay? The plan is to put it on to quarter 3. Anybody else got a question? All righty. So we're actually going to start today with you guys doing a little like work for me. You're just going to fill this in for me, okay? So I'm going to put this up on the board in a second. And let me go ahead. Would you pass these out, Stacey? And all of you onliners, if you can hear me, you're going to find this online. I have to post it real fast for you. You're going to find it in your notes packet. It's just easier that way if you're online. So we're going to okay. So I need to export this as a PDF for those goons. Thank you so much. You do. So for you guys in here, read through this. It says, throughout the day, a buoy at the end of the dock in Bangor, Washington records the height of the tide at various times of the day, as well as a table showing depths over a 12-hour period of time. What I'd like you to do is I would like you to create a graph okay, where you can see time would be your x and depth that says y would be your y values. On your own, I want you to go ahead and just think of what scale you want to make it. What scale would be best on this? There are no marks on the x and y coordinates, so you have to go ahead and make your own scale. Okay, good, delete this, save this as, and one-liners, third period, class of working, create, material, okay. So you people online right now, you're looking to do this page right here on liners. So find that in the page, and you're just going to do this. This. So I'm just curious, on the y-axis, what are you going to let each square equal? 1, yeah, you could just let each one equal 1 here, so I'm just going to go ahead and do that. I'll label it 1, 2. Of course, this is at 0. What about on the x-axis? What do you want to do?
1.
You want to go 1 on that as well? Yeah? I mean, I only need 1, 2, 3, 4, 5, 6, 7. Yeah, so do you want me to go ahead and make this like this is noon, 1 a.m., 2 a.m.? Yeah, that, and I think I created it so you could do that. So I'm going to go ahead and put down M here. So this is going to be midnight. That'd be like 0, 100 anyways, okay? This is 1 a.m., 2 a.m., 3, 4, 5, 6, 7, 8, 9, 10, 11 a.m. This would be noon, and then this would be 1 p.m. I'm just going to put it that way so we have it there. Okay, great. So now it's just estimating. I mean, this next part's just kind of like estimating where these would be at. So at midnight, we're going to be at 3.1. That seems easy enough. Just going to go up here and just let's make this purple. I like purple. Okay. So we're just going to say right about there. Great. So at 2 a.m., I'm at 7, 8. So I got to make sure I go over to 2 a.m. So 7.8. So we'll just say right about there. 4 a.m., 11.3. So we got, here's 11. That'd be 11.5. So maybe right about there. 6 a.m., we're at 10.9. So here's 10.9, right about there maybe. Let's see here. 8 a.m., we're at 6.6. 1, 2, 3, 4, 5, 6.6. 10 a.m., we're at 1.7. 1.7, we'll say it's right about there. And noon, we are at 0.9. Okay, great. So if I connect these, okay, I'm going to go ahead and connect these. Kind of looks like that. If I just kind of connect them. I decided not to just do lines. I like this, like a nice smooth curve on this, okay? So here's my next question for you. What do you think if I wanted to plot at maybe, I don't know, 2 o'clock, 2 p.m., where do you think the 2 p.m. would be at? What do you think? I mean, does anybody have a guess? Do you think that it's going to keep going down? No? No? What if I told you, what do we call, like, this right here, this time up here, we got this, we got this. So we've got these different things. We've got high tide, we've got a low tide, it looks like. So the tide goes in and out, in and out. Does it do that over and over again? And does it take the same amount of time every time? Does anybody know? It changes. It changes based upon like the time of year it is. Okay? But like if you had 2 days in a row, it would pretty much be the exact same as far as the times. Okay? It's just like anything, like, you know, sunrise, sunset, 2 days in a row, they're almost exactly the same, but we know that like in December and June, they're completely different. But gradually, you look at a few days in a row, they're about the exact same. So what if I told you that it's just going to continue this pattern over and over and over again? It's going to continue to do this over and over and over again. And what if I wanted to know what the water was, the depth was at, oh, I don't know, 7 a.m.? What if I wanted to know the depth at 7 a.m.? Well, I can estimate from this what it is right here. I can just go up and say, well, it looks like it's about, I don't know, 8.7. It would just truly be an estimate, okay? So what we would like is we would like to be able, in the future, to recognize and write functions for these types of graph. Okay, now one of the nice things you're going to find out is when you see something that's curved, and what I'm telling you is this actually would go ahead and go back up, and guess what it would do? Then it would go back down again. And it would continue over and over and over again. We call that a periodic function. We call it a periodic function because it repeats over a period of time and does the exact same thing. So we call it periodic functions. When they repeat and do the exact same thing over a select period of time or a select period of X values or inputs, and it does the exact same thing every time, we call it a periodic function, right? So what we're going to do today is we're going to be looking at the first two most familiar, most important periodic functions you're going to learn. Those are sine and cosine functions, okay? Sine and cosine functions. That's what we're going to be working on. So this, today, what we're doing is sinusoidal curves. That's what this unit's about. And you're going to get a packet with notes to fill in, so you don't have to worry about that. But again, this is called sinusoidal curves. I want you to look at this. This is a roller coaster, okay? I believe this one's up in Canada. And I want you to look at this. There's two different tracks. They're running side by side. If you look at this one here, it goes up and it goes down, and then it goes back up and it goes back down, okay? And it continues to do that over and over and over again. And the distance from here to here is the same every single time, okay? It's the exact same. In other words, the next hill down here would be the same distance from this that this one is from this one. All right? And we call that distance the period. Easy enough. The distance between where it starts and stops repeating is called the period of the function. You'll find that out today. Okay? Of course, that looks like a maximum. This down here at the bottom is a minimum. That's keywords we know, right? Okay. I'll give you another view of this exact same roller coaster. Here it is. This is a different angle of it. So here you can see, woo, here's that one. And see how they're over and over again? You've got 1, 2, 3. These three right here are repeats. This distance and this distance are the exact same. And then coming back, these are the same distance apart that these are apart. Okay? And it's just following the same pattern, up and down, and your height, your depth, all the same at the exact same periods of time. It's a periodic function. These are called sinusoidal curves. Why? Because they're based upon the sine function. Okay? They're called sinusoidal curves. So today, our goal is to understand the parts of these graphs and what makes them do what they do. Okay, so here we go. For your dining pleasure, I've got these nice packets. I didn't bring any crayons so you could draw. Woo! Damiano, I deliver in 30 minutes or less. How about you? You too? 10 minutes or less? Whoa! All right, so before we go ahead and do anything else, we need to look at this page on here on transformations, okay? Because we need to make sure we remember what these things do to a graph, because they're very important when we're talking about periodic functions. So if you go to that page, all right, so we're right here right now, and I already have them there for you, okay? If you start with a function, so if you start the function f of x, and you multiply it by some value out here in the front, you will have either a vertical stretch or compression. Now, we did that in quadratics, way back with parabolas, okay? We had x squared was a function, and then we had ax squared. We could change the value of a. We could make it positive, we could make it negative, we could make it bigger than 1, we could make it between 0 and 1. Does anybody remember what happened when I took x squared and I put 2x squared in front of it? What happened to that graph? It got like this. What was happening was it was being pulled vertically up. So you stretch it. If you pull it like this, what happens? It gets skinnier. Anything you have, if you have a balloon and you stretch it vertically, it gets skinnier. So that's what was happening when you had a parabola x squared and you multiply it by 2, it got skinnier, it got stretched. When it was a half x squared, it got wider. You were compressing it. You were pushing it down so it widens out. So we call those a vertical stretch or compression. Again, it is a vertical stretch when the absolute value of a, because if it's positive or negative, flips it over. Okay, remember that from quadratics? X squared, negative x squared was this way. If the absolute value of a is greater than 1, it's a stretch. If the absolute value of a is between 0 and 1, it's a compression. Okay? That's what happens. All right, here, this. When you took x and you added or subtracted a constant to it, it is a horizontal shift. Boom, you can see it right here. So it says the graph of f shifted c units to the right if x minus c. So this one right here is c to the right. This one is. This one is c to the right. This one here shifts the graph c units to the left. It's the opposite. Because what it's doing is it's all about the zeros of the function. Okay, it's all about the zeros of the function. That's why it's the opposite. We talked about these a long time ago, I know. Okay, this is a horizontal stretch or compression. If you multiply x by a constant term, it's a horizontal stretch or compression. Okay, so you're going to stretch it this direction or you're going to compress it like this. All right, so how does that work there? What do you think? If you're thinking about the value of k, okay, what do you think is going to happen if the value of k is bigger than 1? What's it going to do? is actually going to compress. It's the opposite. Okay, so here we go. So here it says horizontal compression if K is greater than 1. Again, it's absolute value idea. And it's a stretch if it's between 0 and 1. All right. And then the last one out here, this is nothing more than a vertical shift. It's a vertical shift. This one right here, if you take the function and you add a constant to it, this is going to shift it up b units. Because all you're doing is adding a value to y. That moves it up on the y-axis. And the second one over here, this guy is going to move it down b units because you're subtracting from y. All of these things are going to come into play when we're talking about sinusoidal curves. All right? Sinusoidal curves. So that's a review of transformations, the basic ones, okay? So we have rigid. The rigid ones are the shifts. The non-rigid are the compressions and the stretches. We're going to be getting better and better at those, and we'll see what they do. Now, if you go to the next page, you're going to see all these key terms when graphing sine and cosine functions, okay? So what we're actually going to do is I'm going to do a graph for you here in a second, and then I'm going to like on the graph identify these things so we can see what they actually are, and then we'll write them down. Easy enough, okay? So let me see if it works or not for us today. It's this guy here. And here we go. Oh, escape. Okay. So you can see this says unit circle and sine and cosine graphs. Now, real quick, I have a question for you. So we all know, hopefully, that on the unit circle, that the y-coordinate is the what value? Sine, right? We've talked about this, right? And the x-coordinate is the cosine, right? We've talked about this, guys, remember? Because if you recall, if I were to draw an angle of any rotation like this right here, and I went like this is y, this is x, this is theta, we know that the what? And this is the unit circle, that would be 1. We all should know by now that the sine of theta is y over 1, so the sine of theta is y. We have said that. And the cosine of theta is x over 1, so the cosine of theta is x. We have been saying that multiple times in here. Sine is the y coordinate, x is the, sine is the y coordinate, cosine is the x coordinate, if we're on the unit circle, all right? So, here we go. I want to look at the sine of theta. Theta is the angle of rotation. We start here if we're in standard position, right? Okay, notice x goes between -1 and +1, because it's the unit circle. -1 to +1, all right? We are in radians, so we know 1 full rotation is how many radians? 2 pi, right? 2 pi radians. Okay, great. So I'm going to go ahead and click sine of theta. Okay, now you'll see that this graph is already there. And I want you to follow along, and what's going to happen is you're going to see this angle start to form, and you're going to see this move at the same time. So two things are going to happen at once. So if I start dragging this, we can see that theta, okay, so right now, let's just go back here. Where am I at right here? What is this ordered pair right here? This is at 1, 0, right? That's at 1, 0, correct? What's this at, by the way? Let's just put these down.
0, 1.
This is at 0, 1. What's this at? And this, of course, is at 0, -1. Can anybody real quick, by the way, tell me at pi over 4 where I'm at? What would pi over 4's ordered pair be? Beautiful. Radical 2 over 2, radical 2 over 2. Yeah, you guys agree with that, correct? Okay, real quick, we're just going to do the first quadrant here. What about the pi over 6? What's that at? Beautiful. Radical 3 over 2 and 1/2. And then, of course, up here at pi over 3, we're at 1/2 and radical 3 over 2. And we know when we come over here, we have to just change signs, correct? We should all be pretty familiar with this by now. So right here, I'm at 1, 0. Now remember, so what's the sine of 0 degrees? If I have not even created an angle or 0 radians, what is the sine of 0 radians? 0 over 1, which is what? 0, right? The sine of 0 is 0. Remember, this graph over here is the sine of theta. So tell me, what's being graphed? What are the inputs over here and what are the outputs over here? If this is going to be the graph of the sine of theta, if over here, this graph on the right is f of theta equals sine theta. What are my x values or my input values? What's the input right here, guys? What's the input? What's the domain values? Theta. What's the output? The sine of theta. The input is theta, the output is the sine of theta. In other words, guess what this x-axis would be labeled? Guess what this spot right here on the x-axis is? 0 radians. What do you think this spot on the x-axis is? What? 2 pi radians. What do you think this spot's going to be on the x-axis? Pi radians. What do you think is going to be this spot right here? Pi over 2 radians. What do you think this spot right here is going to be? 3 pi over 2 radians. So in other words, when we're graphing these things, the domain, the input values are theta values. They're angles. They're angles, okay? Great. So now let's start graphing. Here we go. So we know at 0 radians, the sine value is 0. That's why I'm right here. So if I start rotating here, let's say I stop right there. Let's say this is at pi over 6. Let's say this is pi over 6 right here. Then what is this distance here? Wait, what? 1/2. Why? Because the sine of pi over 6 is... All we're doing, guys, is graphing the what values? The y values. That's all we're doing. We're graphing the y values as we go around the unit circle. At every familiar angle, we're just putting down what is the y value. So at 0 radians, the y value is 0. At pi over 6, the y value is 1/2. At pi over, we have to keep going here. At pi over 4, oh, let me move that. At pi over 4, we'd be where? This would be at radical 2 over 2. At pi over 3, we'd be where? Radical 3 over 2, which is about 0.866. And then guess what? When I get to pi 0 over 1, guess where I'm at? So what do you think this point right here is? What is this ordered pair right here? What is this ordered pair right here? The ordered pair. What's the input? What? Yeah, but what is it right there? What is theta? Pi over 2. What's the output? You said it. 1. Now, some people get really messed up here because these are two different things. This graph is related to this one, but they're not plotting the same points. This is plotting x values and y values. dependent upon the angle. This is plotting just the y value dependent upon the angle. All this is doing. Okay? So now, what's going to happen? Let's just keep tracing this and see what happens. Look what happens to this graph. What's happening to my y value now? It's going which direction? Going down. It's decreasing. Look what's happening to this graph. It's doing what? Decreasing. And can you look at this red line? You see how it's going down? It's the y value. It's how high up it is. Look at that. It's going down. And then all of a sudden it does what? It gets here and it hits the axis again. Then what's going to happen to our y values? They're going to be negative y values. And look where our graph's going to go. It's going to go below the x axis. It's going to go down. So if we start going down this, boom, we get there. At 3, 5, and 2, boom, we're down at 0, -1. See it? -1 right here, -1. Then it comes back up, and then guess what would happen? If I could continue drawing this, what would happen? That thing would go around, and this graph would do the exact same thing again. It would repeat this graph. Every time, if I could keep dragging this around and around and around, this graph would just continue doing the exact same thing over and over and over again. All right? Over and over and over again. Now guess what? So this is what the sine curve looks like. It's kind of cool looking. I like it. Kind of like the sine curve. Let me just turn this off real fast. Let's talk about cosine. Look at the cosine curve. Now we should all know, by the way, that cosine is which variable? It's the x. What's the x value here? 1. That's why the graph's starting up here then. Because at 0 radians, the x value is 1. When is the x value 0? Pi over 2. That's this. This spot right here, that's pi over 2. When is the x value going to be at -1? Over here. At pi. That's what this is. This right here is at pi radians that happens. When's it equal 0 again? When I'm down here at 3 pi over 2. That's this guy. And then it goes back, and this is what? Where's that going to be at? And if I trace it, look at it. Oh, I got this pen. That's not one. Watch. Oh, here we go. Notice this time what's it doing? It's measuring the distance. See how it's the x values. And the x values are doing what? This point is getting closer and closer to the y-axis, which means the x values are decreasing. My graph over here is decreasing. Boom. Here's what's really cool. Those graphs are related to one another as well. When you come back, we're going to keep talking about this. When you come back, we're going to keep talking about this.
They do. They have a No, it's not. You got another one right here.
Oh.
And I have that one.
All right, Andrew. Here you go.
Hey, what's up, guys?
You walked in.
I saw that.
Wait, where are the other?
Right under. Why didn't you go?
What am I doing wrong here?
Ready? I think The boomerang is great.
Better, what's up, man?
Nothing much.
How's baseball going?
Good.
Is it good?
Yeah. Straight up. And you should start.
You got a freshman team?
We were supposed to have a game today, but I think it got canceled.
Really?
Yeah.
Have you played many yet? 3?
Once.
1? Because the other teams don't have freshman spots?
Like 9 p.m.
Pretty press. Very passive.
How much was that?
Very passive boomerang. And you should sharpen it so then you can make it a weapon. I mean, no, you gotta sharpen your bit.
Yeah, I already seen
Alright, Brady, you gotta catch this. See if he'll come back for me.
Yeah, it didn't work.
Andrew,
Yeah,
it's supposed to come back. Andrew, it's supposed to come back.
Maybe if I break the other name.
Yeah, Brady.
Frisbee, man. You're gonna go break it more.
Try to throw it at me.
Go break.
As soon as he wants.
Just throw it at me. It's like a battle axe, dude.
Is that literally it?
You should put like metal around it, Andrew. Andrew, you just like put this in metal and then sharpen it. Cut it in however you
I mean, but how are you gonna catch it?
You don't. It goes through your hand.
Touch your hand.
You got your handle right here. It's like
Twist
what
this
though?
to it.
You're gonna die.
I should have thrown it.
Yeah, wake up. How much? What time do you have bed? What?
Yes,
What a guy.
What Tuesday of next week?
What a
What
guy.
time do you wake up? Well, we went to the universe.
Sam was a bit different.
It just never. Did you go to bed? Did you go to bed? I think so. You think so? What are you talking about? Hey,
Alright.
fall asleep on the couch. That was on Saturday, you did? What about Sunday? What did you do? You showered?
But he doesn't remember. But he doesn't remember.
Finished all your, you had no homework. Good job.
But he did government on next Tuesday.
So you got like 2 hours of sleep.
Sam doesn't even know what class he's in.
You got 6 hours. If I get 6, I'm good.
Not 2. That's pretty smart, right?
2 hours is not enough.
No, I don't think it's
But
enough.
it started like right good breaking.
Sleep deprived.
It's terrible. I remember one day we were doing like the what is it, the math thing where it was like the 5 different sections on the computer.
Oh yeah. The
But
delta
I
math.
started doing that at 2 a.m. and I was just like,
I
couldn't do it. I physically couldn't.
He didn't
So I
take that for a break.
I had to go. I went to look by sink and just left a little cold water, trying to make that. I just couldn't do it.
At that point, I had to give up and fall asleep.
I mean, it was my own fault. It didn't start over till.
I know, but I didn't even know we did that. The delta.
What? I know. Because you're just like, oh, I had a long day. I'm just gonna sit on my phone and do nothing.
Yeah, and then it's like 1
And
o'clock.
then it's 1 o'clock and you can sit over. It just makes it worse. You're like, I'm not gonna do it tomorrow.
And then you sleep. You know, I slept till 1 a.m. or 1 p.m. on Saturday.
I slept
all day.
I've been waking. I haven't slept on my lunch.
But it was like I needed it. I don't know.
I slept until 9. Sunday, Saturday, yeah.
They got rid of the hot tub.
Complete, I thought
It's in the dumpster.
Third party got. You want place for the. Yeah.
Don't you guys have a pool too?
I like the other half of bracket, so I think it's like. You in it? Why not?
I didn't want to do it this year, so I just did it. And then I stopped doing it.
Those you get invited.
Are the bells working today? Have they been working the bells? I don't even know.
No.
They haven't been?
Yeah, they have.
Yeah, they have.
They didn't work this morning, but I don't know if they've been working
One
like,
unit. I swear, I heard a bell today.
I don't even know.
The bell, the 7.2 bell that,
Right this morning. Yeah, they did not ring this morning, no. So I don't know.
Gavin said he
It
wasn't
rung
taking
after
races.
advisory and it rung after second.
Okay.
I know.
Yeah.
He knows what I heard you said.
No. Hey, there's a bell. All right. So here we go, guys. So I want you to, so up here we have two graphs. We've got the red one. The red one is a sine curve. I'm just going to tell you that. This is a sine of theta. And this black one here, this is the cosine of theta. So I'm going to ask you a couple questions. First of all, you notice that their shapes are the exact same, right? Okay. Can anybody tell me what this location right here represents? What is that telling me about sine and cosine? In general, what is this telling me right here about the sine of theta and the cosine of theta at this green spot? They're equal. So talk about that now. Over here, where does that happen? Yeah, what angle is that at? It's at pi. This is pi over 4. Because at pi over 4, they're both what? Radical 2 over 2. This spot also is where sine and cosine are equal. Where does that happen a second time? Quadrant what? 3. Down here at what is this angle right here? That's the coordinates, but what's the angle? 5 pi over 4. That's what this is at. Okay. That's kind of cool. Hey, how far apart do you think it is from here to here? I think that distance is in radians. In radians. What do you think that distance is in radians? How many degrees is it from here to here? How many radians is it from here to here? Look. What is it? Pi over 2. From here to here is pi over 2. This distance is pi over 2. In other words, if I took the cosine theta and shifted it pi over 2 to the right, what would happen? They'd be the exact same graphs. They'd be the exact same graphs. Or if I took the sine of theta and shifted it pi over 2 to the left, they'd be the exact same graphs. That's just craziness. All right? Now, so what we're going to do right now is we are actually going, I'm going to just set this over here. I'm going to get this out of here. I'm going to minimize that. We're going to talk about the domain and range. Okay? And I'm going to do some drawings on here, and we're going to talk about these. Okay, so first of all, domain. The domain for sine and cosine is all real numbers. Now, that could be in radians, or it could be in degrees. So there's positive and there are negatives, right? It's anything we want. So the domain is all real numbers, radians or degrees. Boom. The range, here we go. Okay. So for the basic sine and cosine, what was the range? What was the high and the lows on the y values? The lowest it went was -1. The highest it went was +1. So the range on sine theta and cosine theta, we know that the range is what? What is the range? -1 to +1. Remember how we wrote the range in the domain in the past? Interval notation, that's what that is. So for sine theta, cosine theta, the original two functions, the range is -1 to +1. And those represent the unit circle anytime you're on the x or y axis and you're rotating around. That's what those are at. Okay? Boom. All right. Period of a function. For sine and cosine, it's the number of radians / degrees before the graph repeats. Okay? For sine theta and cosine theta, P, which is period, equals, what do we say? When does it repeat? 2 pi radians. Boom. It's 2 pi radians, which would be the same as what degrees? 360 degrees. All right? Again, this is for sine and cosine. The parent functions. The parent functions, sine and cosine, have a period of 2 pi radians or 360 degrees if you want to write it like that. It's either one of those. It's according to what unit we're in. Okay. Amplitude. Ooh, big word, amplitude. I probably should have gone ahead and done this, but here's what amplitude is. Amplitude is half the distance between the max and min. Half the distance between the max and min. Now, I want everyone to think about the graphs I just had on the past. When I did the sine curve, so I was going to put the sine and theta here real fast. Okay? So the sine of theta would look like this. All right? This is the sine curve. That's at 0. That's at 2 pi. That's at pi. This is at pi over 2. This is at 3 pi over 2. What was this high point here? What was that max value there? What was this maximum value here? 1. What was the minimum value down here? -1, right? So what do you think the amplitude of this thing is? And since it's a distance, see how it says distance? Distance is always what? Positive. So the amplitude is always thought of as a positive number, guys. So what is the distance? Half the distance. Well, what is the distance from here to here? 2. So what would the amplitude of this be? 1. Okay? This has an amplitude of 1. All right. Midline. This is a horizontal line which is equal distance from the maximums, the maxes, and the mins. It's a horizontal line that is equal distance from the maxes and the mins. If I were going to draw the midline on this graph right here, it's right here. This right here is the midline. It's in the middle. In other words, from the midline to the max is a distance of 1. From the midline to the minimum is a distance of 1. So it is literally in the middle of the graph horizontally. It's halfway between the maxes and the minimums. Okay, boom, it's right in the middle there. Horizontal line. The last last thing is a phase shift. Phase shift is a shift left or right. So when we're talking about periodic functions, a horizontal shift is referred to as a phase shift. I will probably call it a horizontal shift. I might call it a phase shift still, but that's what it is. A phase shift is nothing more than a shift left or right. Okay? Now, these things, period of function, amplitude, midline, these three here are actually very important in the graphs. Very important in the graphs. This one can be as well. Again, this is nothing more than a horizontal shift. A phase shift is. Okay? So what we're going to do is we're going to sketch some graphs by hand. Okay? We're going to sketch some graphs by hand to try to find out what's going on with the sine curve to start. We're going to start with the sine curve. Okay? And again, we're going to do it by hand. We're going to just do some nice sketches. So, we're going to start with this one, y equals sine of x. If you like y equals sine of theta, that's fine. I don't care what you put. It doesn't matter to me. But what do I know? X is a measurement of an angle. Y is what? The sine of the angle. Okay? So, real quick, I'm going to draw a circle for myself. Okay? And I'm going to put my familiar angles on here real fast. Okay? And I know this is at 0, this is at pi over 6, this is at pi over 4, this is at pi over 3, pi over 2, 2 pi over 3, 4. So when we graph these, here's what we're going to do. We've got a horizontal line. All this is the unit circle, literally. If I were to take this unit circle and cut it and unwind it, it's just 0 to 2 pi. It's the unit, it's the angles. It's just taking this thing here, and if I literally cut it right here and opened it up and went spring and opened it up, I would have 0 here, 2 pi. They would join together at the starting position. So I'm just unwinding the circles, all I'm doing. So my x-axis is now going to be radians. So I've got 0, 2 pi. Of course, right here would be pi. Half of between there and there is pi over 2. Here's 3 pi over 2. This would be pi over 4. This would be 3 pi over 4. This would be 5 pi over 4. This would be at 7 pi over 4. And then right in here, this would be at pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, 11 pi over 6. All I've done is literally taken this circle, uncut it, and shoot, stretched it out. Now we need an axis. Okay, here we go. So this now is my y value. And this is the sine of these angles. So now we're going to go through this and we're going to just sketch this by hand. That's all we're going to do. So when I start off, I say, okay, what is the sine of 0 radians? All I'm asking you for is the y coordinate. Remember that, guys. It's nothing more than the y coordinate at the angle. So what is the y value at 0? 0. Okay? Now, by the way, this is going to have a max of 1 and a minimum of -1. Right here, of course, would be 1/2. Right here would be -1/2. I can estimate those. All right, here we go. So the sine of 0 is 0. What is the sine of pi over 6? Right here, guys. What's the sine of pi over 6? 1/2. Boom. Got it. What's the sine of pi over 4? it's radical 2 over 2. Now here's the deal. Radical 2 is about 1.4. So 1.4 divided by 2 is about 0.7. So I know that this is going to be up right about maybe there. I'm estimating. It's about 0.7 is what it is. Okay? All right, now I'm at pi over 3. So now I'm right here. What's the sign at pi over 3? Radical 3 over 2. Okay? I'm going to tell you that's about 0.87 is what it is. So it's getting real close to 0.9. So I'm just going to go ahead and bring it up to right about here. It's not to the top. Here's 1. It's not quite that high. Pi over 2, the sign value is 1. So now I'm at my maximum. There it is. Here's 1. All right. So now I'm going to start coming back down. I'm going to be working in quadrant 2. So look, this graph was increasing as these y values were increasing. Now my y values are going to decrease, so these are going to decrease as well. When I get to 2 pi over 3, its sign is the same as pi over 3. So it's this 0.8 something, so it's right about there. 3 pi over 4 has the same sign as pi over 4. So it's going to be right about here, at that 0.7 something. This one right here, 5 pi over 6 is the exact same as pi over 6. It's at what? 1/2. And then pi is going to be at, what's the sign at pi? 0. All right? So this is quadrant 1. That's Q1. This part is quadrant number 2 I just graphed. When I do quadrants 3 and 4, all the y values are what? Negative. So my graph here is going to be what? Below. It's going to be all negative values now. Okay, let's do this. What's going to happen when I get right here at 7 pi over 6? Right here. Negative 1/2. About right there. Great. What's going to happen then? 5 pi over 4 is going to be about negative 0.7. About right here, maybe. Excuse me. What's going to happen when I get to 4 pi over 3? Yeah, it's negative 0.9, so it's going to be right about here, maybe. It's going to be just, I think I'm down lower. That's okay. What's going to happen at 3 pi over 2?
1.
Yeah, negative 1, right? It's going to be right about here. There it is. And then what's going to happen? It's going to start coming back up and repeating those values. 5 pi over 6 is the 0.9. 7 pi over 4 is the negative 0.7. 11 pi over 6 is the negative 1/2. And then at 2 pi, I'm back at what? 0. So then I get this part of the graph. Guess what this is? From here to here, this is quadrant 3. And then this part of the graph is quadrant number 4. And then what would happen? The graph would continue doing the same thing over and over and over again. The graph would continue doing the exact same thing over and over and over again. Now, let's look at this, okay? The midline of this is right here. Here's the midline. The midline for this equation is y equals 0. That's how you write the equation of a horizontal line. Y equals something. The midline here is y equals 0, okay? Amplitude. Amplitude is the distance from the midline up to the maximum or from the midline down to the minimum. So this distance here is the amplitude. This is also the amplitude. What is the amplitude in this particular problem? Yeah, it equals 1. Both of those equal 1. The distance from the midline up here is 1, or from here to here is 1. Okay? And then the period of this thing is from here to here is what? This is the period of the function. How long it takes before it goes through what is called one cycle. This is one cycle. The period is how long for one cycle? Equals the number of radians / degrees for one cycle. And in this particular problem, it's what? 2 pi radians. All right? Okay. Does anyone have any questions how we got this graph right here? Literally, all we were doing was graphing off the unit circle. We were graphing the what? The y values at every familiar angle. We were turning it over here. Okay? This is going, I know this is something completely new for you guys, but I know that you guys can do this. All right? So, your next page, let's see what's on your next page. I want to make sure, that's what I thought. Okay, so, if everybody looks at their next page, you're going to see this. Okay? I want everyone to look at this because you'll notice it says sine and cosine, and all of these have these variables, A, B's, H's, and K's. So, the first thing I want you to know here is that this is your angle. This is like theta. I could have put theta here maybe so it would have been less confusing, okay? So, y equals A times the sine of B times theta minus A, blah, blah, blah. And then this is a y equals A times the cosine of B times theta minus A. Okay, great. So, there are 1, 2, 3, 4 extra values on this compared to the sine or cosine curve. I want everybody to realize that those 4 values right there, those 4 variables, are the same as these right here. Notice in the front of yours, there's a little a, right? That's like this. This is on that inside, theta plus or minus something. Here, this is that value in there. And then this is that b value you have in there, and this is the value of k on the outside. I want to see what each one of those things does to my graphs. So we're going to do this. You're just going to follow along with me right now, okay, on this. You're going to follow along. And all I want you to do is to think about what is happening to my graph as I change the value of A, or if I change the value of B, or if I change the value of H, or if I change the value of K. All right? So let me go ahead. I'm going to call up this line equals sine of theta. Okay. And let me get this set up so it's nice. Whoa, there we go. So we're going to be working right now in radians. Oh, let's have our steps be pi over 4. Oops. Okay. So I'm going to call this over here. So everybody, you're looking at this right now, okay? So if I drag this over, I want you to look right here. So here, you just graph this with me, okay? Notice it says sine of theta, boom. All right, great, here it is. So if I click here, 0, 0, and then, of course, if I start going up here, if I get to pi over 4, look what it is, about point, that's not pi. There it is, boom. We keep going up. There's that point, there's pi over 4 right up there, 0.71 we said. And we're going up, and then we get this, and then we come down, and we get this, boom, boom, boom. And if I zoom out, what do we notice? It continues doing the same thing over and over and over again. And what do I notice? From this spot here to this spot here is how many radians? 2 pi. And then from this spot to this spot is how far? 2 pi. Look at this, by the way. How far is it from this maximum to this maximum? 2 pi. What about from minimum to minimum? How far do you think it is? 2 pi. So this is where the graph starts repeating. Bottom, top, bottom, top, bottom. I mean, it's repeating. Here's a question for you. How far, if the period from here to here is 2 pi, what part of the period is it from the minimum to the maximum? What part of the period? If minimum to minimum is the full period, what would minimum to the maximum be? Half the period, exactly. Or maximum to the minimum would be out what part of the period? Half the period, okay? All right, we'll turn those things off. So, what's the amplitude of this? 1. Where, if I wanted to graph my midline, what should I graph? Y equals 0. Let's do it. Let's put it in there. Let's make it a different color. Let's make it orange. Oh, let's make it actually green. There it is. Great. Love it. Done. Okay. So, what I'm going to start with here is I'm going to put the letter A in front of this. Okay? But we're going to see what this value of A does to our graph. All right. So, you're going to tell me, how is the graph changing? And let's go ahead and we'll zoom in on this graph right now. We're just going to zoom in on this part of it right here. Okay, here we go. So, I'm going to start dragging it to the right. What is it doing? As A is increasing, what is changing on my graph? It's stretching it, right? So what is changing is the maximums and the minimums. Now, here we go. So when I was at A equals 1, what was the maximum value? 1. If I go to A equals 2, what's the maximum value? 2. If I go to A equals 3, what's the maximum value? 3. Okay, is the A value changing where it's crossing the x-axis at all? No, has no effect at all on the x-intercepts. None. The value of A, all it does is it changes the amplitude of the graph. So on the original function here, what was the amplitude? From midline to here was what? 1. If I go up to here, what's the amplitude now? 2. If I go up to A equals 3, what's the amplitude? 3. So guess what the value of A does? It changes the amplitude of the graph. So if we're over here on our notes, right here, A is the amplitude of the graph. I'm going to just write that down. A is the amplitude. Now, I have to be careful. Amplitude. Amplitude. Okay, of the graph. All right? So there's the first thing I know now. And that's true for either one of these. It doesn't matter which one it is. A is the amplitude. Now, amplitude is always positive because it's a distance. Let's go back and look at the graph real fast. Because everything I just did was a positive value of A. Okay, here we go. Let's do a negative value of A. Let's go back to 1. By the way, look what's happening when A goes less than 1. It's doing what? Changing how tall it is, right? And what happens when I go to here? What's the amplitude now? 0.5. If I click this max, guess where it's at? 0.5. All right. What happens if I make A equals 0? It's just going to be a what? Straight line, because 0 times anything is what? 0. Okay, great. Here we go. Now we're going to do negatives. What did it do to my graph? It flips it over the x-axis. In other words, it's a reflection if it's negative. If A is negative, it reflects the graph across the x-axis. But the amplitude is still that value. So in other words, here, what do you think the amplitude is of this graph? Be careful, because it's the distance 2. It's the absolute value of it. Amplitude is always positive. So if A is positive 2, it has an amplitude of 2. If A is negative 2, it has an amplitude of negative 2. So if it's positive, it's regular. If it's negative, it gets flipped over the x-axis. As A increases, my amplitude, the height increases. As A gets closer to 0, what happens to my graph? It gets closer to 0, the amplitude does. All right, so A is nothing more than the amplitude, and it also affects, is it regular or flipped over the x-axis? Okay, any questions on what A is doing to my graph? We all saw that, hopefully. Okay, let's go ahead and get rid of A. Let's get rid of this A value here. All right, let's talk about the value of K. That's an easier one to deal with, okay? So at the end here, I'm going to put plus K. And I want a slider. Okay, so let's go back. Here's the original one. This is my original function. There it is. You can see it. Okay, boom. Great, great. Okay, watch what happens as K increases. What is my graph doing? It's shifting it, right? We said K is nothing more than a vertical shift. If it's positive, it's shifting it up. If it's negative, it's shifting it down. Does it have any effect on the amplitude? No. No effect at all on the amplitude. Does it have any effect on the period? Is it changing how quickly it goes through a cycle? No, it's not. All it's doing is shifting it. So what is it doing? It's changing the maximum and the minimum, though, isn't it? And it's also changing where the midline is. Here's a question for you. If my original graph is right here, okay, Damiano, this question's coming your way. Are you ready?
Yes.
I'm going to take K and make it 1.4. Where's the midline going to be at? Thank you very much. The midline is the value of K. The value of K actually tells you where the midline is. The value of K tells you where the midline is. Now, why is that important? Because if I know the midline and I know the amplitude A, then I know where the maximum is and I know where the minimum is. So for us, K, this value of K down here, K is the midline. Boom, K is the midline. So if I know the midline and I know the amplitude, then I know the maximums and the minimums automatically, guaranteed. Because how do you find the maximum? It's K plus A. How do you find the minimum? K minus A. That's how you find the maximums and the minimums. Okay? Again, the max is K plus A, the minimum is K minus A. All right, great. So both A and K, they have absolutely no effect on the period of this graph. It was a stretch or a shift, vertical. Both of those were vertical things. They affected it vertically, what it did. Okay? All right, now let's look at the value of B. We're going to do B next. So I'm going to go back to my graph, my Desmos here. And I need to click the right thing. Here we go. So we're going to get rid of this. We're going to make this y equals 0 again. Go back to our parent. We're going to get rid of this. And now right here, I'm going to put parentheses B, and then I'm going to close that. Okay, so now I've got the value of theta, B times theta. Okay, so if I'm looking at my notes in the transformations here, if I'm looking at my notes in the transformations, I'm looking at this one right here. I'm looking at f of k times x. This is where I'm at right here. We know that this is a horizontal stretch or compression. Okay, so let's see what happens when I change the value of B. Okay, so let's come back here. Let me get to my graph again. Okay, so I got a slider here. Yes, I want to add a slider. Of course I want to add a slider. I love White Castle sliders. Okay, here we go. So let's go back to 0. Okay, so here's my original one. Now you'll notice that says B equals 0, there's nothing. Why? Because if B is 0, then the angle is always 0, and the sine of 0 would be what? The sine of 0 is 0. That's why it would just be a horizontal line here again. Okay? So let's go up to b equals 1. There's my original function. If you look at it, starts at 0, ends at 2 pi. All right, here we go. I'm going to change this. I'm going to make b larger than 1. And I want you to tell me what's going to happen to my graph. Look what happens to my graph. What's it doing to it? It is vertically, it's horizontally doing what? Compressing it. Somebody tell me what the period of this function is now. Pi. Hold it. So originally it was 2 pi. When I made b2, it went down to pi. What if I make b4? What's the period of this thing now? From here to here. Oh my goodness, it goes from what? 0 to pi over 2. So what is that value of b doing? It's not, is it changing the amplitude at all? As I change the value of b, is it changing the amplitude? No. Is it changing the midline? No. Is it changing the max and min? All it is doing is changing the period of the function. How quickly it goes through a cycle. B changes the period. Okay? And look what happens if I make it negative. It does what? Flips it across the y-axis. It flips it. Now for us, I will be keeping b as a positive value. We're going to be doing positive values of b. All right? So, let's talk about this here. Here we go. So for us, I'm going to actually put a little space in here. That's okay. I can do that. Okay. So we're going to add now, and this, what we're writing up here is true for either sine or cosine. It does not matter. Okay. So we've got these two things. So let's talk about b. Okay. b. What in the world? I just tried to type and it did that. Here we go. B. Why is it doing that? Okay, let's just add it here. We'll just add it. Okay, here we go. B changes the period of the function. Right? Now here's what you have to know. The period equals, are you ready for this? 2 pi to, oh boy, that's not the pi. I can never remember which quick key is pi anymore. 288? Hold on. Oh, here they are. Pi, 227. Okay, here we go. 2 pi divided by b. Why is it 2 pi? Because the parent function sine starts off at the period of what? 2 pi. If you take 2 pi and you divide it by b, you get the period of the function. How quickly will it go through one cycle? Let's check that. If I go back to my graph again, here it is. Here the period is, boom, 2 pi. You can see it. If I make this value 2, what's 2 pi divided by 2? Pi. And look what the period is now. Pi. If I take 2 pi divided by 4, what do you get? What's 2 pi divided by 4? Pi over 2. That's what the period is. Look, 0, pi over 2. So b, the value of b changes the period. What happens if b is less than 1? Like if it's 1/2? Yeah, let's make it 1/2 here. What is, boom. What's the period now? 4 pi. That's because 2 pi divided by 1/2 is 4 pi. B changes the period. B, again, changes the period. Nothing other than that. It's all it does is changes the period. The last one, guess what it is? It's the value of h. Let's just see what h is going to do here. So I'm going to click this. I'm going to click this. Boom. We're going to go here, and I'm going to put theta minus h. Okay, add a slider. So here is the original function. Boom. There it is. If I move it and I make it h plus, it's what are we doing here? It's moving it to the, it's shifting it. It's shifting it. So does it change the amplitude? No. Does it change the period? No. Does it change the midline? No. Does it change the max or min? No. All h does is changes what? What is it changing on the graph? A couple ways you can think of it. One of the big things is it's changing the zeros. It's shifting them left or right, isn't it? It's changing the zeros. It's also changing where the cycle starts. Like here, where's the cycle start right here? 0. If I move it here, where's the cycle starting at now? It's starting at -1. So H tells you where the cycle starts. It's the phase shift. Okay? Add that to your notes. Tomorrow when you come back in, bring this packet with you. We're going to keep going with it. We're going to keep going with it tomorrow. Bring it back.